Fluid coding and AI here. A model can advertise a 256K context window and still be the wrong shape for a coding agent. The real test is not whether it loads, it is whether it stays useful after a real repository, a broken interface, and one misleading tool result. Qwen3-Coder-Next is an 80 billion parameter mixture of experts model with about 3 billion active parameters per token and a native 262,144 token window. Qwen positions it for coding agents and tool use. Fine, but a scorecard is not the lived experience of an agent loop. You experience inspect, run a command, read the result, revise, edit, test. One slow phase can poison the whole loop. The architecture under test is simple to describe and much harder to judge. Keep selected experts and latency-sensitive work on the GPU. Put most weight capacity in host memory. That can make a much larger model feasible on a fixed machine. The trade is CPU memory bandwidth and CPU to GPU transfers. Capacity goes up, immediacy may go down. For an agent, that is not a footnote, it is the product. One distinction matters before any timer starts. Moving model experts or weights into host memory is not the same as KV cache offload. The KB cache is the agent's growing working memory for prior tokens. As context grows, it needs memory too. Both systems can consume host RAM, and both can add transfer pressure. Calling all of that RAM offload is how a useful diagnosis turns into a haunted spreadsheet. Here is where my expectation changes. A maintainer leaderboard lists 20.6 decode tokens per second for Qwen3-Coder-Next in FP8 on an RTX 4090 with 2 EPYC server CPUs. That could feel perfectly usable while writing an edit. It tells us almost nothing about the wait before the first action after a 96K repository prompt. Fast decode and painful long prefill can both be true. That is the contradiction worth testing. So the scorecard needs phases, not one heroic tokens per second number. Record cold ready time from launch to the first completed agent response. Record long prefill time separately. Then measure warm continuation from the last tool result to the next model action. Decode rate still matters, but it comes after first token delay, task completion, and time to a verified patch. The user does not benchmark a completion. The user waits inside a loop. Run two architectures under one fixed hardware budget. First, a GPU-oriented baseline through VLLM or SGLang where the hardware permits it. Second, a heterogeneous SGLang and KT-Kernel or K-transformer setup with host memory model capacity. Hold the host, GPU budget, model revision, quantization, tokenizer, tool parser, prompt, repository commit, and context cap steady. If the same model cannot run both ways, say so. That becomes a residency strategy comparison, not a clean model race. Test 32K, 96K, and 92K tokens. Those are test caps, not trophies. Qwen's own serving examples warn that a 256K default can prevent a server from starting, and suggest 32,768 as a shorter fallback. If 192K fails, the failure is evidence. Report the failed start, timeout, or out-of-memory event, then use the largest stable cap. Quietly dropping to a smaller window would turn a hardware limit into marketing copy. The task ladder starts with the short repair, one failing test, one intended file, and one decoy. Then, a cross-file refactor with the public API change, tests, and docs. This exposes basic tool discipline before long context has a chance to hide sloppy work. A pass is not, it wrote code. The patch must be relevant, the target tests must pass, and unrelated tests must stay healthy. Next comes a screenshot-driven interface defect. Keep browser resolution, capture path, and tool format constant. The agent needs to form a hypothesis, change the code, and pass both a visual acceptance check and an automated test. If the serving path is text only, provide deterministic OCR, DOM, and visual diff output, and call the task screenshot informed through tool output. That is still useful. It is just not native visual reasoning wearing a fake mustache. Then, inject one plausible bad tool result, a stale test failure, a truncated log, a file search pointing at the wrong path. The agent should verify the evidence, revise its plan, and still reach the normal pass condition before the limit. This is a better test of tool use than counting function calls. A confident patch against a decoy file is not autonomy, it is just autocomplete with a wrench. Finally, the real long context test, a pinned repository slice with architecture docs, history, logs, decoy files, and a bug whose fix needs evidence from several places. At 96K and 92K, the question is not whether the model can quote a buried line. It is whether it finds the right evidence, explains the root cause, makes a coherent multi-file patch, and proves it with tests. Long context without selection is just a larger waiting room. For every run, keep completion, timeout, and infrastructure error separate. Record actual prompt tokens, server ready time, prefill time, decode rate, agent turns, tool calls, files changed, test run, VRAM peak, host RAM peak, and any cache eviction or swap activity. Repeat conditions at least 3 times when practical, then report a median and range. Agents are non-deterministic. One glorious run is a demo. A distribution is evidence. The practical verdict has to be conditional. Host memory heterogeneous inference is not automatically bad. K-Transformers documents a serious route to fitting this model with a 4090 class GPU and large host RAM. But published decode speed is not a local agent verdict, and a model benchmark is not a serving benchmark. It is practical only if the fixed rig starts reliably, long prefill stays tolerable, warm turns remain usable, memory pressure stays stable, and the agent reaches verified patches. That is the architecture test. If you want coding agent tests that measure the loop instead of just the leaderboard, like this video and subscribe to Fluid Coding and AI. The next useful number is the one that survives the repository, the tools, and the test suite.